workshop number 3 on the topic of data analysis, where my colleague Dr. Tim Hilkin will walk you through how to conduct an ANOVA test in SPSS.
You'll be conducting an ANOVA when your dependent variable is measured on a metric scale, so interval or ratio data, and when your independent variable has more than two independent groups. For instance, if we consider the data from the Marketing Management Week 2 survey, we could compare the different MRP teams, 3 independent groups, in terms of their ability to relate to the MRP assignment as measured on a 1 to 5 scale. What the ANOVA test allows us to do is to test whether the averages of these 3 groups are statistically different from one another in terms of their ability to relate to the assignment. So what we need for this test is a nominal grouping variable with more than 2 groups and at least 30 respondents within each group. Furthermore, the dependent variable, of course, needs to be at least interval data. And the null hypothesis that the ANOVA tests is that the means of the 3 different groups, or teams in this case, are all equal. And the alternative against this being that at least one of the teams is different in terms of their score on the dependent variable. So this is important to keep in mind, that the ANOVA really tests whether at least one of the groups is different from the others. If we then go to SPSS, we can conduct an ANOVA by going to Analyze, Compare Means, and then selecting the so-called one-way ANOVA. In this case, we want to compare the 3 different teams, which we will then insert as a so-called factor. And we want to compare the teams in terms of their ability to relate to the MRP assignment, which we then include as the dependent variable. Before clicking OK, it's important to go to Options and request the descriptives, so you get the means and standard deviations in the output. And it's necessary to take into account and test an assumption that's underlying the ANOVA, similar to the independent samples t-test, namely the homogeneity of variance test. And as you'll see in a minute, it is also good to include the Welch. If we then hit continue and run the test, we get this output. And if we start at the top, we can see the means across the 3 teams presented here, A, B, and C. And we'll zoom in on the differences, potential differences between the means in a minute. But first I'd like to highlight the test of homogeneity of variances. This is similar to the Levine's test you saw for the independent samples t-test, and it's important that we check this here before drawing any conclusions. The test works in the same way as you saw for the independent samples t-test, namely it tests a null hypothesis of equal variances across the groups and an alternative of non-equal variances. In this case, if we look at the top row, we can see that the test with a p-value larger than 0.05 is not significant, so we cannot reject the null hypothesis of equal variances in this case. That means that we can assume equal variances, and as a result, when we then go to check the p-values of the test of means, we can look at the regular p-value here for the ANOVA. If the test up here, the homogeneity of variance test, was significant and we would reject equal variances, then we would look at, to compare the means, then we would look at the significance value of the so-called robust test of equality of means, which is based on the Welch statistic. But as mentioned in this case, the p-value here is larger than the threshold, and so we look to this p-value here to interpret the ANOVA. Recall that the null hypothesis of the ANOVA was all means are equal, and we can see that with a p-value smaller than 0.05, we can reject that null hypothesis. And what that allows us to conclude is that the means are in fact not equal. Now we might be tempted to directly look at the means up here and simply to conclude that, well, it seems team B has the highest mean, but here it's important to then think back to what the alternative hypothesis that we've found support for here for the ANOVA is, and that's that at least one of the groups is different from the others. And with three groups, we cannot be sure which of these groups is different in a statistically significant way. And to do that, we need to run a so-called post hoc test, which we can do by following the similar procedure, clicking on Analyze, Compare Means, going to the ANOVA again. You can see here, this is what we previously entered. Under Options, it is also saved everything that we previously had. And now we ask for a post hoc analysis. And here is where it's important that we previously ran the test for equality of variances, the Levene's statistic, because the ANOVA, as you can see here, offers a variety of different post hoc tests which are classified according to equal variances assumed and equal variances not assumed. Recall from the previous output that we have equal variances assumed, and in this case, for the purpose of this course, we'll be using the so-called Scheffer post hoc test. If, in your case, when you analyze your own data, you find equal variances not to be assumed, then in this course we'll be using the Games-Howell post hoc test. But as mentioned, in this case, we have equal variances, so I'm going to untick this again. We can then hit Continue, and something that is also helpful for the ANOVA is under Options to indicate that you would like to have a means plot, so a visualization of the means when we now move on to the interpretation. If you hit Continue, OK, SPSS will reproduce the output that we previously had, and in addition it'll offer these post hoc tests you see presented here in the table. And what the table does is display the post hoc tests between the different teams. So it really focuses on the difference in means between the groups in the independent variable, and it does so in a pairwise manner. So you can see here that here we are comparing the mean of team A versus team B. The mean difference is shown here, and to the right there's a p-value related to that mean difference. So in this case, it seems that team A has a lower mean than team B, and this is at best marginally significant though, so we need to be very cautious in interpreting this here. What we can, however, conclude is that the difference in mean between team A and team C, where team A, based on a positive value here, seems to have a higher mean, is, based on a p-value smaller than 0.5, significant. And SPSS conveniently also includes a little sign here to indicate that. Now if we go through this in a pairwise manner, we've compared A against B and A against C. That leaves B against C, and we can see that in this case B has a higher mean than C, and that is also statistically significant. And this is also visualized very neatly in the means plot below, these differences that we just took a look at. Now if we wanted to draw an overall conclusion and formulate a very concise conclusion, we need to look a bit in the table which of these contrasts offers us the the easiest way of reporting the results. And the way I would do this in this case is to indicate that starting at the bottom, so to say, Team C clearly has a lower mean than Team A and a lower mean than Team B in terms of their ability to relate to the assignment. And then kind of moving up, we can furthermore see that, however, Team B has a higher ability to relate than Team A, but that difference is only marginally significant. So in sum, and then if we look at the figure, we can say that both teams A and B feel that they're better able to relate to the assignment than Team C, and we have some indication, marginally significant, that Team B might be somewhat even more able to relate to the assignment than Team A.